How's it going? Are you in your new place now? I remember you had some move going on.
I am in my new place. I am finally in my new place on a Saturday. For like the past 2 months, I spent weekends at my old place packing things up.
Okay.
Now, also, when you have Verizon Fios, they let you move your account to a new house, but doing so, before they turn it on at the new place, they turn it off at the old place.
Mm-hmm.
So when I was at my old place, I had no TV or internet.
Okay. That must be very strange, right? These days to even spend one day without the internet.
And last weekend I also didn't have any furniture, so. So the last weekend I went there Saturday, did something by my house, slept on an air mattress, and then on Sunday the movers came back and moved all my books, which they left the week before when they moved my furniture.
Okay.
So I presently have 52 boxes of books in my living room waiting for me to sort through.
Oh, wow.
And I had to go through 12 of them last night to find TAOCP.
Okay. So I guess to go along with those 50 boxes of books, you have 10 boxes of shelves as well, right?
I have one room dedicated to being a library.
Sounds really nice.
Yeah, I counted up 30 linear feet of bookcases. So like going around the room, 30 feet of bookcases.
Yeah. Hi, Michael.
And then after I had this all set up with the 30 feet of bookcases in that room, my sister says, "Wait, you have a big house now. You have room for the family piano." So,
Okay, we'll give people maybe another 5 minutes. And I did see a couple of new names again on the RSVP list. I don't know if they'll show up. Just one. So this is the plan for today. There's this little section on mathematical induction that I felt is probably a good time to do this because we'll probably be seeing that being used in a lot of the tree-related algorithms and theorems and properties. And then we'll just go back to where we left off last time, dealing with threaded trees and a couple of algorithms. So I seem to remember, Michael, that when we were looking at one of the algorithms, I think it was the in-order traversal where you pointed out that the head node could have used a null pointer instead of pointing back to itself.
I don't remember.
Okay,
what random comments I may have made in the previous.
You don't want to be held accountable to anything.
In the words of Bart Simpson, it wasn't me. I didn't do it. You can't prove a thing. Nobody saw me do
it. In this age of social media, no, that's not likely anymore. Everything is online now. Anyway, we'll look at it when we get back to the trees section.
Seriously, what are you talking about?
So there was an algorithm in which we had threaded trees, and there was a special head node that had one of the link nodes pointing it back to itself. And I think you brought up the point, or you raised the question, like, why couldn't that be null?
Oh, right.
So, and I looked at it briefly after the session, and I think it's because that's just the definition of threaded trees, that the links are never null.
Okay.
So,
like I said, I like my answer better. My answer, I think, was Knuth preferred infinite loops to null pointer exceptions. So.
Okay. Hey, Miguel, how are you? Okay, I think we can just go ahead and start a minute or two early. So as I mentioned, we are going back to chapter 1, just for this one preliminary section on induction. And this is, it starts around page 10, and we'll just read the first couple of pages, spend about 5 minutes on that. Okay. Was this an easy refresher? Anything new or different from what you may have known before?
Yeah, it's old stuff to me. I've done this a lot.
That's great. That's great. Any problems with the equation that was being proven? The sum of the odd numbers equals n squared. Everyone follow the little proof?
Yeah. I was a bit disappointed he didn't try doing the two up top. He gave his examples.
Which one?
The second line under 1, 2, 1. For example, P of n might be n times n plus 3 is an odd number.
Oh, that one. Okay.
Yeah, I was like hoping he was going to do it on that.
Okay. Can we do that quickly?
Okay. 1 times 4 is an even number. That works.
So what? Just to make sure everybody's following this. So we are trying to prove using induction if n is at least 10, then 2 to the n is greater than n cubed. That's the statement on the second line of 121, page 11. So for n equals 1, no, so this would be starting at 10. So 2 to the 10 would be 1024. 10 cubed is 1000. So yeah, that is true. What's next? Probably need some pen and paper for this. I have to expand out a cubic. So that's the cubic on the right hand side. for n plus 1. Anyone got it yet?
Okay, I was working on the first one,
Okay.
which was that. Now I'm thinking n squared is going to be even, 4 is even, 5n will be odd when n is odd. So, and the other two will not change that. So this one will fail.
So you're saying it's not true?
Correct. Well, that's like the first one.
For which n is it not true?
That's the earlier steps.
Could you walk us through this?
Okay, so we're saying that for P of n, n times n plus 3 is even.
You're doing the other one. I was looking
right,
at the
yeah.
second one. I guess I misunderstood you.
Right. Okay. So you put 1 in here, you get 1 times 4, which is in fact even, which works. We then put n plus 1 in, and if you want to go through the calculations, you get n1 plus n4 even. Multiply that out, you get n squared plus 5n plus 4 is even. N squared is even. 4 is even. 5n will be odd when n is odd. You add 2 even numbers to an odd number, you'll still get an odd number. So that fails.
So for which n, I mean, all you have to do is to provide a counterexample. So which n are you saying it won't be an even number?
I'm saying it fails for n plus 1.
So it fails for 2, for n equals 2?
Okay, so n equals 2 is 2 times 5, that works. 3 times 6 works.
I mean, if you're trying to disprove the statement, all you need is one specific value of n. We don't need to go through induction for that.
But I'm saying going through induction, it fails. No.
If you wanted to disprove something using induction, I'm not sure how that would work, because that's, yeah, I'm not sure how you would use induction to disprove something. I haven't really thought about it that much.
Okay, so if we throw out induction and just look at the formula itself, n times n plus 3, you'll always have one even number and one odd number. And an even number times an odd number will always be even.
Okay, but all you have to do is to provide one value of n, and then the statement is disproven. So, I mean, if you're reasoning it out using some properties of even and odd numbers, then all you have to do is to find one value of n that fits your reasoning and just use that. So which n would that be?
Right, yeah, so I'm saying if I ignore induction, just looking at that, I'm pretty sure it works. It is true. even though the value will come up through induction suggests it may not be.
Okay. So if it's true, then can you prove it using induction? We already established that it is true for 1, for n equals 1. So now can we, assuming that it's true for n, all the way to n, right, 1 through n, can we show that it is true for n plus 1?
Now, I believe I did my, my cross multiplication here correctly. Substituting n for 1 for n plus 1 for n in here, multiplying that out. I think I got that right.
Okay, yeah, so n squared plus 5n plus 4 is what it comes out to be, just like you said. And so why is this always even?
I don't know. The 5 in the middle, the 5n in the middle, should be odd whenever n is odd.
Can we use the fact, the induction hypothesis, can we use that? So can we plug in what we know due to the induction hypothesis that for 1 through n, n times n plus 3 is even. So what if we write so we write n squared plus 5n plus 4 like that, and then we get n times n plus 3. Like that, right? And then by the induction hypothesis, n times n plus 3, we can assume is even. And then you're adding that to 2n plus 4, which is obviously even. So then the result is even. Does that work?
That sounds good to me.
Any other questions or comments? Okay, so let's move on to algorithm I, which is at the bottom of page 11. And it kind of goes all the way through page 13 to the bottom of page 13, just a few lines above where algorithm E starts. So that's what we're reading for about 5 minutes. Hi, Arthur. Just reading. We have a couple of minutes. Okay, any thoughts on algorithm I and how it relates to induction? Why do you think he's done it this way? He's provided this sort of algorithmic formulation of induction.
Well, I'll weigh in, even though I just showed up. Algorithm I is a way of it's an algorithm for producing a proof where the proof itself will not be inductive, right? Or a proof for any given case of a statement. It's not a proof of the general case, but it's a general algorithm for producing specific proofs. And I think that in general, he finds and hopes his readers find that sort of algorithm to be easier to reason about, maybe, than this abstract idea. Or it's just another way of, if the abstract idea doesn't immediately catch you, look at it as this algorithm.
Yeah, I can buy that. Anyone else? Yeah, I also have the same feeling, especially the sentence just after the flowchart, the figure 2, where he says, since this algorithm clearly presents a proof of P of n, the proof technique consisting of steps A and B is logically valid. So yeah, so I think he's making that sort of constructive argument for the more abstract statement that is introduced in the beginning. And there is some explanation towards the end of the section as well that I didn't read in that much detail, but it seems like there are some other benefits to this as well. Anything about the geometric proof or the Fibonacci sequence towards the end of the reading? Okay, so let us then finish up the rest of the section. So this is algorithm E all the way to the end of the section. It's about 7 minutes. Okay, did everyone get through at least the proof for the algorithm? So anyone care to summarize it? It's a little tricky. I think it's more than a little tricky, actually.
Well, I don't know that I really traced through the whole proof, but I believe it. Looking at the flowchart in Figure 4, as he says in the text later, the really creative part of the proof is assertion A6, right? Like the point of this section is if you have a program or an algorithm and you want to prove it's correct, one way to do that is to add assertions along the edges of the control flow graph and say, when we get here, this is true. And then when we get back here, it's still true. But for example, you know, the timer T has counted down and we're closer to finishing than we were before. And eventually we get to 0, or, you know, eventually the algorithm terminates, which, as he said, is usually handled separately. But it's preserved this property that we started with because it's preserved every time we get through this part of the code. And so when we get to the end, we have a solution. Right? It terminates and it has preserved this invariant. And so he's annotated all of the invariants in Figure 4. And he says basically A6 is the only important one. It's the only one he would really annotate in real life, and then the rest are sort of mechanically derived from it.
Yeah, that's a great summary, and I guess it goes back to equation 6. You know, that paragraph where he says the problem is to prove that this algorithm works properly for all m and n, and then trying to figure out what, you know, because in the induction statement there's always this n. What should that n be in this particular case? And yeah, so I guess he's given a nice way of discovering what that n could be by looking at each individual step, and then sort of narrowing down like which is which steps are the most problematic in terms of preserving some statement before entering that step and when you leave that step. And then as long as you're making progress towards termination, then it's a proof. Any other comments? Has anyone come across this reference, the bottom of page 17, where he mentions Dijkstra's work on discovering new algorithms that are guaranteed to be correct if you start from the specifications of the desired output and work backwards?
Short answer, no.
Okay.
I'm not. I will be interested to see what that is, and we should look that up.
Yeah, you should definitely look that up. Yeah, it is very interesting. And Euclid's algorithm, by the way, was one of Dijkstra's favorites. he did a lot of things related to Euclid's. In fact, I think he even has an efficient, you know, version of Euclid's algorithm that is credited to him. Okay, so let's maybe look at one exercise or maybe two from the end of this section, just to get our hands a little dirty. We did look at a couple of statements that are at the very beginning of 1.21 before you joined, Arthur. So we did worked through a couple of those, but let's look at some of these exercises. You want to try number 9 on page 19? It's a rating of 20.
All right. So we're proving by induction here, and he doesn't say it, but induction on n, right? N is the one unbound variable going on here. So suppose n is 0, then 1 minus a to the 0th is 0, and 1 minus 0a is, wait, I'm sorry, 1 minus a to the 0th power is 1, and 1 minus 0 is 1, and so the base case is true. And then, given that that's true for n, then we have to prove the inductive case for n plus 1. So we take the left-hand side is greater than or equal to the right-hand side, and we multiply the left-hand side by 1 minus a, and we subtract just plain a from the right-hand side.
Okay, how are you able to do that?
Because the right-hand side had been 1 minus n times a, and now we're going to make the right-hand side 1 minus n plus 1 times a.
Okay.
And so we're subtracting 1 additional a from the right-hand side.
Mm-hmm.
But on the left-hand side, we're multiplying by 1 minus a. And so I see that this should work. How do we turn this into words that prove it works? Right?
If you're multiplying the left-hand side by 1 minus a, where a is strictly less than 1, right? It's a positive number, strictly less than 1. Then 1 minus a will also be less than 1. So you will get something smaller than what you had before.
Both sides are getting smaller, and the right-hand side is getting smaller faster. Because after the base case of 0 is true because both sides are 1. And then when n equals 1, then we have 1 minus a on the left and 1 minus a also on the right. And so that will be some number between 0 and 1. Not equal to 0, not equal to 1.
If we multiply both sides of the inequality by 1 minus a, then on the right-hand side, we'll get 1 minus a times n plus 1 plus na squared. And a squared will be definitely less than a, because a is between 0 and 1. So
That does it. If you multiply both sides by 1 minus a, and on the right-hand side you have, oh, gosh, it's hard to do without drawing it on a blackboard.
yeah, let me write it down. I did write it down on my notepad. Oh, James has it. Okay, so
1 minus n plus 1 times a, and then you have this na squared term that's plus, but that doesn't matter because on the smaller side, you can, if I guess you could write it out as saying, oh gosh, I always hate less than and greater than proofs with induction. They're hard.
So just the statement for n plus 1 is what James has, right? It's
Where does
1
James have it? I don't see anything.
mine in the chat.
Oh, I gotta open the chat.
Yeah. 1 minus a 1 minus n plus 1.
1 minus a. What?
So that's 1 minus n minus a, the right hand side.
P of. So write out P of n. P of n is 1 minus a is greater than, or 1 minus a to the nth. Oh, that's okay. Yeah, kind of write it like this. Oh gosh. I don't see where your exponents are. So
I'm using the caret as an exponent.
you have so if you start with that and then you multiply both sides by 1 minus a. Then you can say that left-hand side is 1 minus a to the n plus 1. Now you can multiply out the right side. And if it's greater than, and so that's almost that one. Oh, I forgot it. I forgot the a there after the n. What I just wrote is wrong. It should be. Should have an a in here, like that. So this is the n plus 1. Wait, where did I get a 10? That should be 1 minus. Oh, my fat fingers. Try it again. This is what you get after doing that math. You get, this is almost what you're trying to get to, 1 minus a to the n plus 1. This is almost pn plus 1. You've got this extra na squared term.
Mm-hmm.
The extra na squared term is in the right direction. If it's greater than, we've shown that 1 minus a to the n plus 1 is greater than the right-hand expression plus some positive value. Therefore, it's got to be greater than 1 minus n plus 1 times a, by the definition of what greater than is. In other words,
I buy that.
I guess the way you could write it is like this.
All those greater than should be greater or equals, but it doesn't change anything that makes sense to me.
Oh, so we're going, okay. Well, it would be 1 minus n plus 1a. Yeah, like this. So what I wrote there, whoops, it's not going, yeah. So if you look at that, if I put in another greater than sign and just took out that na squared term, the NA squared is always going to be positive. So so if you subtract it, you're going to get something that's smaller. Right? That works for me. I don't see any problem in that logic.
Okay, I'll need to review this, but yeah.
I got a lot of typos in there, which is a blackboard would be better.
Yeah, it's also harder to work with the superscripts and the subscripts. So it's a little confusing. Okay, so let's now move back to where we were last weekend. And this is section 231, page 327.
Is this volume 3 now?
No, this is still volume 1, but back to the trees.
Okay.
Just further into the same volume.
Okay.
Algorithm I.
There's algorithm I. It's on 325 in my book.
Oh, okay.
I was kind of assuming the algorithms were in alphabetical order. And on 327, well, on 326 is algorithm A. So I kept going forward, further and further forward.
They are not in alphabetical order.
Okay, if somebody could explain this algorithm. What are we trying to do here? No explanation?
Well, I'm still trying to figure out the syntax, which apparently you guys covered last week. Which
Yeah. So there is some notation. So there is the whole concept, which is about 3 or 4 pages earlier, and then there is this notation that's actually 1 page before threaded trees are defined and introduced. So in my edition, it's 321, but I think that you're like a couple of pages behind, so probably like 319. But yeah, so Q dollar with the dollar refers to in order traversal. And if the dollar is before the node, then that's a predecessor. If the dollar is after, then that's a successor. But predecessor and successor in terms of that particular kind of traversal, whether it's in order or post order or pre-order. So the idea behind the threads is that you would directly link a node to one of these ancestors or descendants that would follow in that particular traversal order. So then you don't have to, actually do the traversal anymore.
right.
So here we're trying to insert into a threaded binary tree.
Yes. So R link and L are the left and the right link of the tree, except that it's a threaded tree. So when you're at a leaf, R link and L link are the threads. And if you're at a tree that you can be at an internal node that only has one child, in which case one of the links is a thread and the other link is the actual child. You can tell which is which by R tag and L tag. If R tag is 1, I think, then the R link is a thread. It's not the actual descendant. You're at some kind of a leaf or a partial leaf of the tree. So that's the notation. And then the other notation, which I totally object to, is the Q dollar thing.
Mm-hmm.
But Q dollar is what is Q dollar is, like Zatar said, it's the successor in order traversal. So it's the thing you would think of in order traversal is the natural order. of the tree if the tree was representing a sorted list. So Q dollar is the successor, which is hard to get to if you don't have the stack of the tree and you're at the rightmost leaf, or at the rightmost leaf of a child. If you're at the left, if you're at any leaf, I mean, if all you have is the node, how do you know where to go if the nodes are empty? Well, in a classical binary tree, a leaf node, if you're at the bottom of the tree, if you're at a leaf node, if you don't know where you came from, how do you get to the next node? And because you have this threaded structure, the next node is where the link to the rightmost descendant of your leaf would be. That's the thread, and it'll point to the next one. You just follow that link.
Michael, can you walk us through step 1, I1?
Step 1,
yeah.
Set. Okay, so step 1 is, so Q is the node that you're inserting, and you have to assume that R link and L link are just garbage. Okay, so it's saying take the right link of the node that you're inserting. So you're going to make what you want in the end is you want Q to immediately follow P. So because it's a threaded binary tree, the easiest piece of the you got to do a few things, but the easiest piece that is going to happen is that right link from P. It might be a thread, or it might be a link to other children, but it's got to have to point to Q by definition, because you want Q to be the immediate successor of P. So that first step just sets the right link of the tree to point to the new node Q.
And why is the tag the same as P? Why do you assign?
Well, the tag. Okay, so so what's going to happen is if the node P, if the R link on node P is a thread, then in the end, the R link on node Q is going to be a thread.
Mm-hmm.
And if the R link on node P is a child, we haven't fixed this up yet, but we're going to take that branch of the tree and attach it to Q. So the R link on P is going to, the R link on Q is going to be whatever it was on P. So that's pretty simple. So we take the tag from P and move it to Q, because we move that link, whatever link we moved from P to Q, it's going to be either a thread or a link to a piece of the tree. So it's the same thing. So whenever we move a link like that, if we're copying it, we have to copy both R link and R tag, or we have to copy both L link and L tag.
Okay, so step I1 essentially takes care of almost all cases except when R link of P was a thread.
Right.
And that's the adjustment you have to do in I2. And could you explain that? I think you already did, but
if our tag of Q is 0, that's because we moved it from P. We have to go to Q's successor, and that would be by L link of Q's successor, which.
Why does he say this step is necessary only when it's an internal thread, and it's not needed when it's a leaf, when it's a new leaf? Okay, it's 3:17, so we are a little over time past our break time. So let's take a 10-minute break, and we'll come back and continue our discussion.
Oh.
Okay, we're back.
Okay, I got a good way of saying that.
All right.
Here's what's going on in that last step. If P was an internal node, because it's an internal node, it must have somewhere in the tree some thread pointing to it. And now you're inserting Q, and whatever node in the rest of the tree pointed to P with that thread must now point to Q, because Q will be the immediate successor of that node where it was P before. That's what we're trying to do in step 2. So in order to find that node, P dollar. Go through the algorithm, and the algorithm is described above. P dollar, you go basically to the right link and then all the left links until you get to something that doesn't have a left link. That's the node where the thread was. When you get to that node, you'll find that the thread points to P. You need to change it to Q. That's all it is.
Okay. Yeah, that makes sense. There are some exercises that he has mentioned. Actually, he mentions a lot of exercises in this particular section. There's a lot of material. I think that really needs to be fleshed out, just because you have all these different cases. But one exercise that he particularly recommends is number 17, where he says, we looked at algorithm S the last time for just getting the in-order successor. And he's asking, can you do something similar for the other two kinds of traversals, pre-order and post-order? Actually, he only, in 17, I guess it's only P star, which is pre-order. So using the same threaded links, how would we get the pre-order successor? Yeah, it's P star.
Where are you reading?
Exercise 17, page 332 in my edition, the new edition. So pre-order is node first, then left, then right.
Right. So if you have a left child, then the left child is your successor in preorder. And if you don't have a left child, but you do have a right child, then the right child is your successor. But if you don't have either, then you want to follow your right thread, and that will get you where? That's as far as I.
The right thread will get you the in-order successor, I believe. Yeah. The right link, sorry. Right thread, I guess. That's also fine.
The right link, if it's a thread, will get you to the in-order successor.
Yeah.
If it's a link, it gets you to the top of a tree that has, on the left branch, would be your successor.
So in-order successor would be the right subtree.
Yeah. Well, in-order successor is the successor. It's the very next node.
Yeah, it is.
But the R link, if it's a thread, will be the successor. If the R link is a thread, it'll be the successor. But if the R link is not a thread, it's the top of a tree. It's the root of a subtree, and the leftmost element on that subtree is your successor.
But how do we use that to get the preorder successor?
The preorder successor. Are we changing the threads around?
No. It's the same threads. That's the whole idea, is that the threads are defined, as far as I understand it, the threads are defined using in-order relationships, but you can use them to get to any successor or predecessor in any order, except it's not as easy with pre-order, and post-order, he said, is the most difficult one. So we want to use the in-order relationships that have become more efficient using the tags and the threads, but we still want to be able to do a pre-order traversal, in particular find the pre-order successor. Okay, Arthur has posted a whole set of steps. So if P has a left child.
So the first two steps are the easy ones. And then it gets tricky. But certainly you want to, so if P has left child, you're done. If it has a right child, you're done. Otherwise, follow the right thread. And that gets you back up to the root of the subtree of whose left, so well, the root of the, whatever you want to call it, and it has a left subtree and a right subtree. And you were somewhere, P was somewhere in the left subtree. So at this point, you're doing a pre-order traversal, so you've already visited this node Q that we just got to by following the right thread. Q has already been visited, all the left subtree stuff has been visited. Now it's time to visit the right subtree of Q. So if Q has a right child, that's the one you want. And if Q doesn't have a right child, then it must have a right thread, and you follow that right thread, and you get to another Q, and if it has a right child, that's the answer, and if it doesn't, you follow its right thread, and so on. And I think that gets you what you want, but I'm not 100% sure.
Okay, so anyone has some insight into eliminating whatever the percentage of doubt exists so far? Okay, well, we can think about it. Let us move on to the following discussion on similar trees and equivalent trees. So this is, it starts with the last paragraph on page 327, and then all the way till algorithm C on page 329. Okay, so could somebody explain the difference between similar and equivalent trees? And there is a sentence where he says, some computer applications involving tree structures require an algorithm to decide whether two binary trees are similar or equivalent. If you're familiar with any application like that, that would be great to know.
Well, similar would be having the same structure. So for each node, each corresponding node between the two trees would have the same number of left and right nodes. Equivalent would be similar plus having all the same content in each of the nodes.
Okay, can you think of anything where these would be important? Like the distinction would be important, or the need to compute similarity or equivalence would be important?
I can't really think of anything now.
Well, when a database needs to come up with a query plan, if it's running two different queries, you can look at so the query plan can be broken down into subtrees, whether they're binary trees or not. That you can make them into binary trees. And if you're doing two queries and you've derived the query plan for the first one, you need to see that that tree is similar, or not similar, equivalent if you can use the same query plan on the second one. And furthermore, even if the trees are not equivalent, you may find subtrees that are equivalent. Same would go through for something simpler, I suppose. If you're just trying to evaluate an algebraic expression, it can be represented as a tree. And if your job is to evaluate expressions and you come up with another one that has an identical tree, you could cache that, and you wouldn't have to go through all the multiplication and division again. You just return the cached result if the trees were equivalent. And
I think that's a great idea. Yeah.
Identical. And if the trees were equivalent, then your code for doing the multiplication still works, but it has to take new parameters.
Yeah. So speaking of trees representing algebraic or arithmetic expressions, what about parse trees? Could there be applications there?
You mean like a compiler?
Yeah, something like a compiler where you've got an abstract syntax tree. Once you've parsed
the same idea would apply, I suppose. If you could recognize pieces of the program that had identical trees, you could probably optimize the code for space by putting those trees into what would be a subroutine, even if it wasn't written that way.
Yeah, that sounds very useful.
It's very useful.
Yeah. Okay, what about Theorem A and Lemma? Well, Theorem A essentially. What's the significance and utility of Theorem A?
Theorem A, when I was reading it, I said, oh, this function L of u and R of u equals 1. That was just R tag and L tag in the algorithm. And I was thinking that, and then he says it later on down below line 13. That's exactly what it is.
Mm-hmm. So. And what's the benefit?
So it gives you a way of deciding that the trees are similar if, as you go through the nodes, they have the same tags, same L tags and R tags.
Yeah, it's a way of sort of serializing the shape of a tree into a linear sequence of bits.
Yes, exactly.
And then store and compare pretty quickly. It also seems to me that you could use this to find subtrees that, like Michael was talking about. You could find subtrees that were similar.
Similar, yeah.
By doing basically a string search.
Not
taking 2 bits at a time as your characters.
Yeah, you don't know. It doesn't say anywhere that the U1, U2 are in any particular order.
Well, they're in preorder.
Does it say that? Oh yeah, in preorder. Okay.
Yes.
Okay. In preorder.
You could say that. You could say that. But yes.
Is that sufficient? I'm not convinced, but it could be.
I think so, because all of the leaves are going to have 0, 0. Right? L and R are both going to be 0 for leaf nodes.
No, they're going to be. Wait, aren't they going to be 1? Well, whatever. They're going to be.
The tags are 1, but the L and R is 0.
Right, yeah. You got it. Yeah, if it's that's by definition. You got it. Yeah.
And in fact, that leads into Lemma P, where at least the first part of Lemma P, where he's saying that if you let f of u be L of u plus R of u minus 1, then if you have a tree and you add up all of the f's of all of its nodes, you get minus 1, which is really just a way of saying that if you add up the number of edges in a tree, right? Because L is 1 if there's a left out edge, and R is 1 if there's a right out edge. So you add up all of the out edges of all of the nodes, and you subtract 1 for each node. Then you have number of edges minus number of nodes in a tree equals -1, which is true. Lemma P is more complicated than that, and I'm not going to try to explain the rest of Lemma P, but I noticed that right away. That
Okay.
yes, in a tree we have exactly n. If you have n nodes, you have exactly n-1 edges. And so, given any bit string, I guess one of your Theorem A bit strings, I could look at that and tell you instantly, like, okay, that looks like it ought to be a tree, or that looks like it shouldn't be a tree. You know, like a lot of bit strings would not represent trees because they would have too many ones in them.
Yeah.
Okay. Yeah, the paragraph right after the proof of Lemma P. As a consequence of Theorem A, we can test two threaded binary trees for equivalence or similarity by simply traversing them in preorder and checking the info and tag fields. Why wouldn't that work for the other traversals, for inorder, for example?
I'm not convinced that it wouldn't work. Are you
Okay.
convinced it wouldn't work, or?
Well, I'm just wondering, why is he just mentioning preorder then? Unless there's an exercise somewhere. Is there some
I think
efficiency
preorder
benefit for preorder?
Preorder turns out to be easier to prove prove by induction, because you start at the root node and then you go to the left and then you go to the right. So if you can prove it, yeah. If you can prove it for a tree of size n, then you know that it's true on the left tree and the right tree, and on the right, left and right child, and you can prove by induction that it must be true on the next level up.
Exercise 24 is asking, what if you do in order? I'm pretty sure that it's easy to prove it. Like, of course, it can be post order. Right? Pre-order works, post order works, because you just sort of flip the bit string around. In order, I think, is not entirely obvious. I think it should be true. Anyway, exercise 24 is prove it, and it's marked M20.
What I really found surprising on Lemma P was the last part of that equation where, well, the first part of the equation, they all add up to -1. Which I don't understand what that means, but I totally buy it when you look at it by induction. But on the last part of the equation, the last half of the equation there, it says take everything but the last node and apply your f to it, and you're going to get something that's greater than or equal to 0, which means it has to be either 0 or 1. Because if you add f, because if you add f of n to the, so take the case of k equals n-1. I guess is what I'm thinking. That has to be either 0 or 1. Because you're going to add f of n, and f of n can only be
the specific case of k equals n-1, that has to come out to 0, because
nope, it can be -1.
Is the f of u sub n, where u sub n is the last node in the tree, the rightmost node in the tree, and the in preorder.
The rightmost
thing to be traversed in preorder has to be a leaf.
Oh, preorder. You're right. Okay,
Yeah, this is
that
preorder.
very, very last node is going to have an f of -1. So if you add up everything except that very, very last node, you know it's going to come out to 0. But the node right before the very last node, I mean, you can have the sum of the f's go pretty high, arbitrarily high, as you do the preorder traversal. You know, if I have a very bushy binary tree, that's a complete binary tree down many levels, my preorder traversal is going to hit the very root node and add 1. Its f is going to be 1. And then it's going to hit its left child, which also has right and left children. So it now the sum of the f's is 2, and the sum of the f's will be 3, and so it will go up. But eventually I'll have to hit all of these leaves. For every 1 I'm adding, there's got to be a leaf somewhere to soak up the other end of that edge. And so f is going to go up, and then it's going to go down, and it's going to eventually wind up at -1 once I've hit all the nodes, because there's going to be a lot of leaves in there. The more branches I have, the more leaves I have to have.
Okay, let's wrap this up with this last algorithm. Algorithm C. It has a few steps, but I don't think it's as complicated as some of the other stuff.
The answer to exercise 24 is no, and he shows 2 trees with 5 nodes each that have the same Fs, or the same Ls and Rs for their nodes in order traversal.
Oh, wow.
On page 569 of volume 1.
Okay, so copying a binary tree. Is this something that you would have come up with if you were just asked this? How would you copy a binary tree?
Well, on C2, I would have started with the left instead of the right, but that's just me. I think it would be the same either way.
Okay, but this, he says it'll work for threaded, unthreaded, or partially threaded
Yep.
trees.
Yeah, I was trying very hard to understand whether he was using a stack or not, and he doesn't specify. He does say that you have to go to the successor of P and the successor of Q, but he doesn't say how. If it's threaded, you're gonna be able to do it by following the thread. If you don't have that thread, then you're gonna have to keep a stack as you're going down the left and right subtrees.
So he does point that out after the algorithm. He says,
Yep.
Yeah, if it's unthreaded, you will need a stack.
So when he goes to the right and then to the left, he's starting at.
Yeah, I don't really see any good reason to go right and left. It's arbitrary, but I don't think it has any benefit that I can see.
Well, it probably has a benefit of the same reason you count for loops down to 0 instead of up to n. Somewhere along the line, when you do it in M-mix, it probably has that.
Yeah, that's something I did notice right in the beginning. When he lays out the structure for the node, he seems to prefer placing the right link before the left link.
I don't think it matters in this case.
Yeah, but the more natural thing or the more common way is, left, right, left, right, instead of right, left. So that is interesting.
I guess maybe, I mean, this is kind of a super reach, but maybe it's more cache friendly to touch the left subtree, given that the next thing you're going to do is descend into the left subtree if there is one. So maybe you set up the right, set up the left, and then descend into the left. I don't know. I think it's random. Arbitrary.
Okay.
And what did he mean by partially threaded tree? Is that defined already?
Yeah, so that is, go ahead,
if you have
Michael.
the R links but not the L links, then you can go forward but not backward. That's partially threaded.
Okay.
Yeah, partially threaded is, I think it's synonymous with a one-sided threaded tree. So you choose to either have, the R links representing the threads or L links. And he points out that page 327, just before the last paragraph, that in practice, one-sided threading is much more common. And additionally, he says that the right threaded binary tree is the more common one.
Because that's going forward. That means you can go forward through it.
Yeah.
But you can't, it's difficult to go backward.
Yeah, I didn't go through all of the exercises, but I wonder if he brings up any applications of these things in any of them. So, yeah, if something catches your eye, we can discuss them the next time. But the threads do come up again and again in future sections, so I'm sure we'll be seeing some more uses. Okay. Next meeting, we are just going to continue with the next section. And there is an interesting application of the algorithms in the next section, which has to do with calculating derivatives of an algebraic expression. So that should be interesting. And yeah, so just next Saturday. That's it. Thanks a lot for attending.
All righty.
Thank you, Satosh.
See you.
I hope I'm saying your name right. I'm
Yeah,
trying.
you are. You are.
Okay, great.